All right, in Canvas here. Now, first I changed your assignment due date for the OWL to Wednesday, and that take-home quiz thing till Wednesday. Yeah. So I modified the due dates from Sunday night to Wednesday. I probably will not go into OWL and change it because there is no late penalty in OWL. Okay, so I might, but I had them matched up before. So there is no late penalty in OWL, only in Canvas. Remember, you have to still submit, right? You still have to submit. Textbook, I had a question on textbook this morning or last night. So here is where I put a complete PDF of the textbook. So in Canvas, once you scroll down a little bit, you see COTS chemistry. Here's the complete textbook. Here is an ebook that you get when you buy the OWL code, and that's pretty good. So that's kind of shortened version, but here's a complete PDF of the book. Okay, let's see if I'm going to make sure I got to change screens here now, I think. I don't want to end. I don't want to do that. Oops. Okay. Let's do a little review real quick. So I'm going to pick one out of here. I'm just going to do 16. So how many meters are in 7 yards? It's going to look something like that. I know right away I need to put a yard down here. And it doesn't matter how many steps. Please don't go and look up to do everything with one conversion. Try to think of what you know. What comes to your mind? What do you know for this? Well, hopefully 1 yard, and you can go 3 feet if you want to start there. Then you can go 1 foot is 12 inches. Then hopefully you're remembering this now. 1 inch, 2.54 centimeters, and I have the unit I want left. Oops, no, I don't, because I got to get 2 meters. .100 centimeters down here, 1 meter. We could shorten that all up. There's multiple ways to do this. We could have went 1 yard to miles and miles to feet. It doesn't matter how many steps you take, as long as everything you have in here is a true mathematical statement. And then all of your units just need to do this, right? The one you're looking for is left. Now, calculator-wise, let's say you have something that in your calculator to punch in, and I think I can go with the previous example we did. Let's talk about using your calculator efficiently. If I have something like this from page 8, let's say that none of these are cubed. To put this into my calculator, I'm going to hit the division key 3 times. So I would go 1.5 times 10 to the 8. I'd say divide by 10, divide by 2.54, divide by 12 equals. If you have numbers on top, and let's say I had a, I don't know, 3.281 up here. I would go this number times 3.281. I would hit integer equals. Then I'd hit divide by 10, divide by 2.454, divide by 12. Is the most efficient way to do it. Otherwise, I see students go this times this divided by this times this times this. It doesn't work that way. You cannot go this times this. Okay. Then they'll go, well, I'm going to multiply these 3 in the bottom. So they'll go divide by this times this times this. It does not work. If you have 3 numbers in the denominator, hit the division key 3 times. Okay. We should be talking about significant figures right here. Now, significant figures, what we're really talking about is how many good numbers do you have? How many good numbers do you have? How many are placeholders? So we're just going to identify how many good numbers we have. So if you have 48 centimeters, the 1's place, 10's place is good. We've got 2 good numbers there. 306.2. This is called a trap 0, but that 0 would count. That's 4 good numbers. And 1329, that 0 doesn't do us any good. We've got 3 good numbers. 7,100 grams. This is like my carbon dating example of dinosaur bone of 3.5 million years old. Those zeros at the end of 3.5 million do not count. This 7,100, those zeros do not count. This is 2 good numbers. So then I type this up. It says this. For number 4 above, to 3 significant figures would be 7100 with a line over the 10's place. That would be 3 good numbers then. If it was 4 good numbers to the 1's place, you have to put a decimal here like this. Then counting numbers are unlimited. Now remember, when you measure something, you are estimating, typically you're estimating the last digit, right? The last thing you write down is an estimate. So you're driving down the road, you look out in the road, out in the field, and you see 8 cows. Did you estimate a part of a cow? Did you estimate the ending of the cow? No, you have 8 cows. So counting numbers have unlimited significant digits. 8.000, there's 8.00000 cows, right? Exact conversions are unlimited as well. The one biggie, again, is 1 inch is equal to 2.54 centimeters. That's a weird one. That's an exact conversion. Or if you said 1 meter is equal to 100 centimeters, right? That's 1.0000 meters equals 100.0000 centimeters. All right, in number 5, this is how many good numbers? We've got 4 good numbers, right? Number 6, 5 good numbers. And number 7, how many good numbers in number 7? 3, right? 3. Because if you put this in scientific notation, you wouldn't write these first 2 down. So this is 4.32 times 10 to the minus 3 if you put this in scientific notation, right? Now, number 8. This 0 right here is not going to count if you put it in scientific notation, correct? What about this last 0? Good one? Yeah, this is a good one. Otherwise, why would they type it on a piece of paper? Why would they write it down? So that's similar to, I think what I said last time, is if it is spot on, and if you use this ruler in lab, which you are going to do next week, every measurement in centimeters should have 2 decimal places. And if it's spot on the 21, it would be 21.00. So you would write the zeros down, they mean something. So this is 1, 2, 3, 4, 5. If you have it scientific notation, you only write down the numbers that matter. So this is 2 and 4. All right, let's go to the next page here. Now, what do you do with these numbers for mathematical operations? (11 through 14) is addition and subtraction. Now, I looked at that, or we looked at that before when I said we were adding up that triangle, and I lined them up, right? So I had something like this. I had 3 digits. I don't remember what the numbers were at all. But if you're lining these up to add, you don't know what that digit is. You don't know what that digit is. You don't know what that digit is. You would round your answer to 1 decimal place, right? So for addition and subtraction, it's the least number of decimal places for your answer, if you have decimal places. Otherwise, you got to keep going left. So I did the water example. And we had like 730 milliliters. This is only good to the tens place, right? So you got to keep going left. If it has decimal places, it's really easy. So in this one, in number 11, we've got 2 decimal places. Is the least here, right? So if we round this to 2 decimal places, that 6 is going to boost it up, right? So we are going to get 28.32. And for units, centimeters plus centimeters plus centimeters, you're still going to have centimeters, right? (12). This is 3 decimal places. So if we did 3 decimal places here, we're going to take a look at this 5. That's a 3. That's going to stay a 5. Yes. Okay. So we're going to get 122.605 in grams plus grams plus grams. The units grams. 13. 1 decimal place. 1 decimal place. 63.9. This is the ones place. So we'd have to do the ones place here. So 76 milliliters. Okay. For multiplication and division, you round your answer to the same as the least. You round your answer to the same as the least. So we've got 3 digits here. We've got 2 digits here. And we've got 3 digits there. The least being 2, we come in from left to right. till we grab 2 digits, which is right here. We're going to round this to the tens. Since this is a 3, this is going to stay at 6. We would get 160. And then centimeters times centimeters times centimeters. Centimeters cubed. 3 good digits there. That 0 counts. All of these zeros here count. Otherwise, the person would not have written them down. So that's 4, and this is 4. So our least is 3. Again, coming in from left to right. We get to the third one here. So that 1 keeps that as 6. 32.6 centimeters cubed. The division here, 4 and 4, huh? So if we round this to 4, .895 meters squared divided by meters. Meters times meters, meters squared divided by meters for a unit. Still going to leave us with meters. This parenthesis is outside the cube for units here. This is just 4.93 divided by 18.71. Come in at 3 sig figs here. And that 4 keeps that a 3, right? So we're going to end up with 0.263 centimeters squared. Centimeters cubed divided by centimeters, centimeters squared for a unit. Okay, 4 sig figs here. 3 here. Trying to come in and round this to 3. We're going to round to the tens place. We round to the tens, 1530. Or 1.53 times 10 to the third would do the same thing. And then millimeters times millimeters, millimeters squared, right? In number 20, this is a division here, and this is in brackets. You would do this first. So this has 3 sig figs, that has 2, and this has 4. So it's all multiplication and division. So we're going to round this to 2. Those zeros do not count. That 4 is going to keep that an 8. So we get 0.0048. Or 4.8 times 10 to the minus 3. And my units, this millimeters over millimeters is going to cancel. I'm going to end up with meters. Okay, operation with sig figs. I know there's an OWL question out there that's just goofy. It puts something in the denominator like 6.3 minus 1 over 10,462 or some goofy thing like that, right? It's something crazy. It's something crazy. This isn't going to do anything. you can't subtract, you can't take 0.63 and go minus 0.00000. Somebody tell me to move up the screen. 000, something like that, 1. That's not going to change anything. Okay. Somebody pointed this. This is the goofiest setup I've ever seen. The camera's way over here and then it's over there. And so if I'm not on the screen, somebody there. Okay. Let's move on a little bit here. So some stuff directly out of the textbook. I guess we better have a definition of chemistry, huh? Composition product, properties and interactions of matter. And a little bit with a scientific method. Somewhere along the line, you've all done the scientific method experiment. All right, classifying matter. So we know the kinetic molecular theory of matter helps us interpret the properties of solids, liquids, and gases. Anything that occupies space has mass, matter. Definite shape and volume, solid. Fixed volume takes the shape of the container, liquid. And by fixed volume, you know, if you have a gas in a syringe, drawing the syringe the best I can here. Maybe a terrible looking syringe. You know you can compress a gas, right? You are not going to compress a liquid or a solid. Now, you got to talk a little bit about mass versus weight. When you step on a bathroom scale, it works because the scale is between you and what? The earth, right? So the earth is trying to push you through the scale. And the scale has numbers. And if you dig a hole 10 feet deep, put the scale down there, it still works, right? Because it's trying to push you, pull you towards the center of the earth. If you go to the moon and take a bathroom scale, the bathroom scale will work. But if you weigh 120 pounds on Earth, you're going to weigh 20 pounds on the moon. Because the moon is 1/6 the mass of the Earth. So it's not pulling you down as much. In science, we have to do mass. Your mass has to be the same, no matter where we measure it. So if you had a teeter-totter method measuring device like this on Earth to mass this dog, you had to put 1 kilogram on there. As long as you know this is a standard kilogram, it says 1 kilogram on it. If you took it to the moon, you'd still have to add 1 kilogram to get this to balance. Even though the gravitational pull on both sides is 1/6 as much, you would still have to put the same mass on there. So when you do mass, you are always comparing it to a known standard mass. Always, always, always. So it used to be a nightmare to get an accurate mass. You would have to do that teeter-totter method. You would have tweezers and you'd start putting these little metal cylinders on there first, and then you'd be down to these little ticky things. It took forever. And you didn't touch these with your fingers or you get oil on them. Now, the electronic balances we use will measure the mass, but every time you move it, you would have to recalibrate it with a known standard mass. So here's how this would go. We could ship a balance, the same balance to Eau Claire, Wisconsin, and ship it to Denver, Colorado. Denver, Colorado, your weight would be slightly off. Mile High City, right? So what you're going to do is you would actually have one of these standard masses. It would be in a box like this. You'd put gloves on because you don't ever want to get oil on your skin. And in each location, you set that standard mass on there. Internal computer calibrates it and says, yes, that is 1 kilogram. That is the only way to get the same mass readings no matter where you are in the world. There still has to be a known standard mass. Okay, let's talk a little bit about types of matter. For types of matter, we can have a pure substance or mixture. If we have a pure substance, it's going to have a definite composition, and it cannot be separated by physical processes. We are going to have an element or a compound. Element, periodic table, right? Copper, aluminum. Or compound, salt, water. If we have a mixture, homogeneous or homogeneous, uniform throughout, or heterogeneous. Now, you may have seen a word like this when you were young, because the word was this. Homogenized. Where did you see that? Milk carton. You ever seen homogenized milk? This is on the milk carton, yes? Right. If they did not homogenize milk, what would happen? The fat would separate, right? The fat would separate. Now, I got to help you guys out a little bit to prove that to you. So we know the fat would separate. So believe it or not, years ago, this is what they did. They delivered milk like this, and it had this top on it, and that's where the fat would float up to the top. What a novel idea. We would deliver a glass container, take it back, wash it, and deliver it to thousands of other people. The same container we would reuse and reuse and reuse. What a freaking novel idea, huh? Instead of putting plastic everywhere. I got to help you out even more a little bit. Now, all mammals have different amounts of fat. We know that this right here is your skim milk cow. Skim milk cow. This cow right here is a 1% cow because it's only got a little bit of black on it. 1% cow. This right here is a 2% cow. Another 2% cow. Here's your whole milk cow, right? That's whole milk. Whole milk cow. If you still think I'm bullshitting you, there's your Oreo cookie filling cows, right? Oreo cookie filling. And of course, I blew it. I did all this ahead of time and I forgot your chocolate milk cow. And your chocolate milk cow, of course, would have to be a what? Does anybody know? Would of course be these, right? Huh? Now, all that truly is BS except for this. Those on the screen have about 4.5% milk or fat in their milk. And the black and white ones do have about 3.5%. These do have more fat than milk. Every mammal has a different amount of fat content, including humans, and a different amount of lactose sugar. And all of that would take to the top. Yes?
We don't forget about like another type of cow species. Well, it's a Merino's Belgian blue bulls, which look like
there's all kinds of them out there. Okay, let's go to the next page on this. So let me switch over. I don't even know if that showed up on the screen now. I don't think it did. So I think what I just presented, if you look at the recording, I don't think I switched the screens. So, okay. Then just some chemistry terms. If we do a physical change, if you do a physical change, you're not changing the chemical composition. So, H2O, solid. Ice, right? If you do a physical change, you get H2O liquid, right? And then you could have H2O gas. That versus a chemical change would look like this. This might be some of the vehicles that I would drive. This would be maybe the shiny vehicles we would drive, but obviously this isn't iron anymore. This is iron oxide, right? A chemical change. Okay. And then I put molecule down here. Two or more atoms joined by chemical bonds. We'll talk about that in the next chapter. Now we're going to talk density. First off, when you're reading a graduated cylinder, you're going to read it at the bottom of this meniscus line, right? At the very bottom, you're going to estimate the last digit. So if we read this off, what do we got here? We've got 20, 21, 22, 23, 24, 25. We're between 21 and 22, right? So we have 21 point. So you're kind of estimating 10 ticks between there, right? So you've got 21 point, I don't know, 7 work? Close to 7? And then milliliters. All right, let's talk about some density. We know that density is equal to mass over volume. All your densities are on your periodic table. So if I zoom this in, density right here is this number. Okay, so the densities are on your table. You'll be using that to look things up. Something that's very, very dense should have a large mass in a small volume, right? And an element that's very dense, of course, is gold. Here is 19.3. And if we go to the left, you can actually see 21.5 for platinum. Gold, platinum, pretty heavy. You may think, well, lead's pretty heavy. And lead's not even close to being that heavy. Okay, lead here at 11.34. So density, mass divided by volume. Typically, this is in grams. This is in cubic centimeters. It probably will also be in milliliters. Now, I do not recommend memorizing any formulas. Actually, babies drink formula. We work with equations and relationships. I like to say we work with relationships. You have to memorize what unit you have. If you don't know what unit, you can't do the problem, right? So I don't want you to memorize these equations at all. Not at all. Here's an example. Okay. Let's say we know that the density of gold is 19.3 grams per cubic centimeter. Okay. Then we know the volume of our object is 225 cubic centimeters. We're looking for a mass. I don't want you to memorize any formula at all. If you are looking for a mass, what unit are you looking for? Grams. So the first thing I would do is you look at the units. Are you going to add or subtract to find the answer? No, why not? Because the units don't match, right? So the very first thing I would do is I try to just throw those together and multiply. So if I threw those together, and I would have 19.3 grams per cubic centimeter. Now, here's what I always say, and I should have stressed this. Start with your single unit number first. This is a single unit number. Start with your single unit number first. Won't these units cancel out? Right? I didn't memorize any equation. I'm just going to multiply those two numbers. Why do I multiply those two numbers? Because when I multiply those two numbers, I'm showing that the units cancel out and I end up with the exact unit that I'm looking for without memorizing any equations. So mathematically, I know I'm just going to multiply those two numbers. And I'm going to get grams, which is a mass, right? Now let's take it the other way. Let's say that it's on the next page. Let's say now you have a mass of 225 grams. You've got the density of gold again at 19.3. We're looking for a volume. Again, memorize units, not formulas or equations. We know we have to get cubic centimeters. And you know we're not going to add or subtract to solve this. Start with a single unit number. So to solve this, I'm going to start with 225 grams. And I should put grams of gold on here. 225 grams. Now, bring in your double unit number. This is my double unit number, correct? Okay. Now, this is grams per cubic centimeter. If you want, you can draw a line all the way over. And how many cubic centimeters? One, right? Now, are you going to put this just the way it is of grams times over cubic centimeters? Will that work? I'm going to write it here. Don't write this down. This will not work, correct? Because my units would be grams squared over cubic centimeters, correct? junk. So do this. 225 grams. And what you'll see me do is you'll see me do this and write the word flick. This is a true mathematical relationship. Every 1 cubic centimeter has a mass of 19.3 grams. It doesn't matter if we flip these units, right? It doesn't matter. Sometimes you put 1 foot on top and 12 inches on the bottom, or vice versa, depending upon what you start out with. So I'm going to flip those units. I'm going to put 1 cubic centimeter, 19.3 grams, and look what happens. I didn't memorize any equation or anything. Have to memorize units. And if you're taking a chemistry or physics class, this technique works all the time. Start out with a single unit number. And it might work just the way you have it. Otherwise, flip it if you have a double unit number without memorizing any equations. Okay, let's do the density. Let's do a density problem up here. This will be similar to what you're going to do in lab. Obviously, you need a mass and a volume. To get your mass, set it on the balance. If you have a regular shaped object, if you have a perfect cube, a perfect cylinder, something, you can measure the volume with a ruler. If you have something that is not perfectly symmetrical, we have to use water displacement. So in this case, how does yours show up? Do you have it printed out in black and white? Can you read that?
Not really.
Not really? All right, so let's see. It looks like it's right there. So what do we've got? We've got 10, 11, 12, 13, that's 14. So let's call this 13.5 right there. Nope, and they've got a 13.5 right here. The initial is 13.5 milliliters. You put this rebar in there of this mass, and the final volume goes up here to 22.4. So that gives us the exact volume. So my volume here is going to be 22.4 milliliters.
Up or down?
What's that?
You can't see.
Oh, sorry.
Thank you.
22.4 milliliters minus 13.5 milliliters in my volume, right? So that's going to give me what, 8.9 milliliters? So my density is going to be 69.658 grams over 8.9 milliliters. Now, Sig Fig wise, and then I see students do this. They'll say, oh, well, this only has 2 Sig Figs in it. So after they put the rebar on the balance in the chemistry lab, they'll just chop this down to 70 grams. You don't do that. Whatever the digital scale gives you, you always write those numbers down. But this answer here then should be 2 Sig Figs, right? You've got 5 Sig Figs in the numerator, 2 in the denominator. So this would be 7.8 grams per milliliter. Is the rebar made of iron? pretty darn close, right? Looks like it is. 7.8. Yes, it matches. It looks like it is. Okay, let me show you some. Let's see if I can do this right this time here. If you open up this document, Word doc, again, anytime you open up a document, and you're gonna want to print the next one out for Monday. When you open it up, it opens up as a Google Doc. Download it to Word. There's going to be a down arrow in the upper right or under File. Download it to Word, or it's not going to look like this, and it's not going to print nice. But there is some, there's some links here then that you can look at here. And I've also got them down here. So now, so this, first of all, the density of water is 1. Anything less than 1 should float. Anything greater than 1 should sink, right? So let's change this to a brick. Obviously, the darn thing better sink, right? And if I change this to wood, it better float. And aluminum should sink. So one of these here, this one, and you can estimate the density here. If the density of ice is close to 1, right? It's just a little bit less. So if you have ice in here, it's going to look about like this. It's almost going to be all the way submerged. This right here is about halfway up. This density is going to be about 0.5. Okay. If all of these have the same volume, which is the most dense? The one that has the most mass, right? If it's mass over volume and your denominator, the volume is the same, the most dense is going to be the one that has the most mass. If these have the same density, we end up with something that looks like this, where all of the masses are different and all of the volumes are different. Now, next time we meet, we're going to finish this up. It's not going to take, we're going to talk about the densities of plastic. I'm going to show you a few videos, and we will finish this up in the first 10 minutes next time we meet Monday. Again, I changed the deadline to Wednesday for those two. Is everybody getting into OWL? Go through Canvas, then you should be able to get into OWL. Then I will send you, I think I'm done with the next learning guide. It looks like this. It's going to be a printout. I think I fixed up what I wanted to from last semester, and I will verify that and send you an email. Okay, so with that, have a great weekend. Stay out of trouble, stay warm, don't smoke, vape, or get COVID.